Hello,
Great.
everyone. Welcome to another community live stream. Today we have some announcements, and then we will resume one of our traditions of bringing up topics that are populating our thoughts during the time that we do research and during the time that we are working for the institute. So yeah, we want to be very open about this. We want your interaction. We want your input. Leave any comments on YouTube. We can monitor that. If you are not on our Discord and want to keep up to date with announcements and chat with us and ask questions that we can then bring to this forum and address, you can join the Discord server. And for that, there might be a link directly there. Maybe James, you can share that link on the YouTube channel, on the chat, and otherwise, everyone is welcome there. So, would you like to start with some announcements, James?
Yeah. So we mentioned the Discord. I was doing some renovating, so there's some nice new little features we add in there. We might add a bot or two to just like liven up the place and create it as more of a collaborative space where we can actually do stuff. So that'll be quite fun. In terms of announcements, should we leave the announcement of the new workshop till the end, or should we
Sure.
mention it right now?
No, yeah,
Yeah.
we can
So
leave it
you,
to, we can leave it to the end. Yes, it's a bit of a
yeah.
yeah.
Yeah, so we'll leave the anticipation there for those that are watching, but we have our big event that's going to take place soon. So we'll discuss that, and we're gonna bring up a little reveal of what that's gonna look like. So that's the cool thing. And then yeah, I think just generally let's have a bit of a roundtable on what's happening at the institute right now and what we're working on, just to get the collaborative juices flowing.
Definitely. Yeah, we can leave the proper event announcements towards the end, but we can, yeah, as you suggested, do a quick round with what we're working on, what's on our minds, and maybe take some questions from chat or otherwise. Nick, do you want to start yourself?
Just in general, what I've been working on, that.
Yeah, and anything is on your mind. I mean, today is the casual day, so every 2 weeks we're gonna have this more relaxed, more informal discussion. So
Well, on the quantum side, I have been exploring some algorithms, like linear solver. Like there's some multiple linear solving algorithms for the quantum computation that's happening. Like there are at least three that I know of already, and we're looking into how to actually implement them within our framework. You have to implement a bunch of pieces, how to do Hamiltonian simulation properly, how to do arbitrary functions, and so that was been what I've been busy on the quantum side, also continuing on the phase space formulation and how to do different um, probabilistic, evolutions of the quantum systems and how to generally think of quantum system as probabilistic system instead. And by the way, it's like even yesterday, as we were doing some block work with Steven, we were doing this percolation theory study and looking through some papers on percolation theory, and even there we found some uh, mentions of quantum master equations, how they basically there's some link between percolation theory and master equations of Hamiltonian evolution quantum theory. So I kind of want to look into that more deeply at some point.
Can you give me a rough idea of what percolation theory is in its essence? I mean, I understand percolation from coffee, but maybe you can explain it to me in the sense of
So,
maths and physics.
yeah, so as I understand it right now, it's like very simple. There are multiple models, right? We were looking, but the underlying physical idea is that there's some kind of membrane that has some properties, whether with some, I don't know, droplet of water, you can think of it like whether it can move forward with some probability, and how it moves, you can model it on a different kind of lattices, so different kind of networks. You have some links there, and it can move if it has some neighbors. If there is a droplet, it can move, or it can't with some probability. So it's a probabilistic CA kind of. There's some probabilistic CAs which also can be thought of percolation models.
So it's kind of like perturbation theory, but percolation in terms of that it like dissipates outwards, or like there's like a directionality to it. Is there
Yeah.
a connection at all?
Information theory is a little different.
Yeah, it's
like
different.
more
Okay.
like mathematical framework for doing estimation and all that.
But it's not
But
unrelated to coffee. If you think of coffee, water going through some dry coffee or something, it's kind of
Yeah.
the same.
Yeah, percolation refers to, in case people haven't heard the term percolation itself, maybe I heard it because my father was a hydraulics engineer. I was talking about like water and things like that. And but percolation refers to this idea of when water goes through a medium that has that it has pores, so it can actually, it's not just freely flowing, but it's also not waterproof, right? So it's percolate. That means to percolate, right? Basically to get wet. And so percolation is this study. Normally, what I've seen it more explicitly is in the context of network theory, where you have some model of trouble or some model of a flow of stuff of some kind, and then you want to measure how quickly something kind of propagates through a network. And then, so this percolation idea is changing some properties of the network, whether the times scales that these things take and so on. So it's basically
it's like in the simplest models there's like a single parameter, and usually there's the most important thing to study is some phase transitions that happens depending on what the value of that parameter. So it's like a probability of that medium percolating and your water flowing through your membrane. If you just increase your probability just slightly, then it's like start flowing.
Yeah.
Right? So it's
another way to, like what Carl, actually I pasted a nice video on it with in the, I don't know, James, if you want to sort of forward that to the viewers or whatever. This one looks at what Carlos was saying about the kind of network model of it. And I think at the phase transition, it's something like below the phase transition, the connected components are, they're considered small, and above they're considered to be on the order of the size of the system. That's the distinction. So as the probability...
below the threshold, your water always stops, right? At some point.
Yeah.
So it's like a finite limit it can reach. But after the threshold, it can flow indefinitely. And it's like a second order transition that is very sharp. It's not smooth. So it's like the exact value that you have to reach in order for this to happen.
And in the case we were studying, I was hoping that there would be some nice way to find it without having to resort to, because setting this cutoff and all these other things is kind of tricky. So it's like, is there some way to keep adding digits to that number without actually sort of running the CA, like some other kind of derivation of the system? I don't know. I'm just thinking there must be some...
When you say CA, do you mean cellular automata?
Yeah. So the setup we have is like, any one cell in the neighborhood is active. Then the cell in the next row comes on with probability P, and that's the parameter. So we're searching for that P parameter that leads to like, just on the edge between bounded and unbounded growth. Yeah.
Interesting.
And it's
Very
like 0.53, I think. I'm not sure.
Very interesting.
Very cool.
Okay.
Anything else you wanted to tell us about, Nick, that's been on your mind?
I don't know. Those are the most things that occupy my mind. Quantum stuff, percolation CAs, evolution, genetic algorithms, which is like, it's just like we can talk about it, but it's mostly going to be like a teaser, because at some point there's going to be a blog post by Steven about it.
Absolutely.
And it's looking very good.
Great.
Very cool.
I've got some information I can maybe chat about, since it's just like a general kind of ideas free flowing. I was reading a paper about random Markov, let's see, RMB, Markov machines. No, what is RM?
Boltzmann machine.
That's the one. Random,
Yeah.
Restricted Boltzmann machines. Thank you. Okay.
Yeah.
So this was quite interesting. Apparently, Jeffrey Hinton was like quite involved with this early on. This is like more like an 80s type idea with regards to machine learning and that sort of stuff. And it was quite interesting because of this concept that it has with input layers and hidden layers, and that there's this bidirectional connection between the layers, which is different to a conventional neural network where it's feed forward with back propagation.
Yeah.
And I was just wondering if that's maybe been looked at in terms of
Yeah, it was the first kind of network I really studied in depth before, and it was actually kind of before this revival of machine learning in, when was it, 2011 or whatever, 13. Yeah, on my lunch breaks I was like digging into these papers and implementing them and things, and looking at
Like
lectures.
Energy-based methods. I think
energy based.
Yeah.
they resurrected recently. I think. Interesting.
Yeah. The approaches back then were, I mean, so like the basic training algorithm was contrastive divergence. So you do this thing where you want your inputs to create this hidden representation, but you want to be able to kind of reconstruct the input again in the backwards direction, and then take another. So you do like this forward back forward thing. So you have your original input, your hidden activations, your reconstructed input, and then a kind of another set of hidden activations. And there's a very simple kind of combination of those two, that pair on both sides, that gives you your gradient actually. So it's really quite simple. I forget what it is. It's like the transpose of the hidden, blah 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 blah, and you just get this matrix, and then you multiply it by a very small amount, which is your step size, and that becomes your gradient. But usually they were used for doing this, what they called layer-wise pre-training, to get the network in like a good ballpark, and then you would just do backprop, and things still sucked because people were still using sigmoid layers, so you still had the vanishing gradient problem. So like theoretically it's interesting because it's a local learning rule, but at least back then, it wasn't exactly like game changing. And one of the problems was that those negative samples, those reconstructed samples, could sometimes be quite far out of your data domain. So there was this trick called PCD, called persistent contrastive divergence, where you don't reset that little Markov chain. You kind of keep it going, and that was the only trick. So simple trick, but it had some interesting results.
So apparently they use it with nice deep insights kind of concepts, where you might have it as part of this chain of a neural network layer, and then maybe a restricted Boltzmann machine, and you could use it as a piece of like for a bit of auto encoding. But it's a nice tool to solve some problems, and in like larger complicated deep learning pipelines.
Yeah. What was cool about them is that you got a generative model, even if you were doing like a classification task, you could still run the network in reverse and get good samples. Whereas if you train a network for classification, it's not necessarily the case that network will be good at generating samples, hallucinated samples. So that was the cool thing. There used to be this cool demo. It was in Flash, and it was on Hinton's like really old personal page. Like, looked like it was just written in Notepad, handwritten HTML. But he had a little page you could go to and play with, like a little interactive applet thing, and you could select which digit, and you would see it going through the network. Or you could click the class neurons and run it backwards, and make it dream the letters. And actually, that was one of the very inspiring moments where I was like, "Oh, these generative models are seriously cool." Being able to learn the shape of your data and generate samples,
it can perform on MNIST, right? It can do character recognition.
That's what that little applet was doing. So it was just MNIST classification, but you could also generate digits, and so it would be like a little wiggly one that's kind of wiggling around, and it's sort of moving around this little manifold. Wow. So it was moving around that sort of manifold of what a one would be, and then when you clicked a two, it would that one would sort of morph into a two, and if you click the six, the two would kind of like very nicely sort of blend into a six and things like that. So
can we touch on what is the revival of energy-based models? Like, where is it? Why is it sort of having a bit of a resurgence at the moment.
Nick, do you know about that?
Oh, nah. I need to refresh my mind. It's like seems I heard something about it recently. About
Yeah,
Same
I
here,
think
but
it's-
I haven't bothered to check.
So Jan
It's
Leclerc
Jan
was
it's like
on the Lex
Jan.
podcast.
Yeah, probably there. Yeah.
Yeah, and he basically was mentioning that he's been talking about this for years, decades. Like energy-based models is a good system, and it's kind of like a different paradigm to generative AI. And he was kind of saying generative AI is amazing, and what it was able to achieve with like the ChatGPT stuff is incredible, but it's inherently limited if you have to keep if you were to extend that to like its maximum possibilities, like we're kind of there. And then he was explaining how energy-based models is so powerful in its like ability to generalize across like many different potential tasks, but it has its own issues, and there's ways that you have to the way you train it and the way like you sample the data is like the tough part. But like as a model for trying to create predictions or modeling like problems in the world, it's very nice. And I like it because it uses maybe like this bit of this concept aesthetically, maybe just about like the second law of thermodynamics, where you kind of have this like energy state that's the same everywhere, and then as you start making samples, it like adjusts the energy density of the environment, and then that's how it kind of like gets a feel for what's happening. So it's a nice philosophical approach for me. So I'm very keen to look more into that.
I wonder whether, like, instead of saying it's energy based, maybe it's better to say that it's like an information based, so that you try to increase information, lower the entropy. It's like you still kind of try to fit a nice landscape of your parameters, but you try to kind of have more information as possible there, right? To have it in a nice landscape.
Maybe energy and information are the two opposite ends of the space of energy. So if you have energy there where you can identify accurate predictions, that's almost like information, and the opposite of that would be the entropy. So maybe that's one way to think about it.
Yeah. There's always been this. I'm coming from a pretty different background than the sort of computer science-y angle here, but there's been this idea that energy and entropy, or energy and information and things like that, have these sort of Hamiltonian roles depending on their context, like energy being Hamiltonian more traditionally in classical dynamics and in classical mechanics. And the question is, can you think of entropy of a similar, like a similar Hamiltonian quantity, where it's somehow constraining dynamics or even determining dynamics and things like that. So energy and information seem to have this, when you think in terms of, again, I'm coming from the background of dynamics, but when you you think in terms of, you have a system that is operating within some energetic regime, meaning energy might be conserved, so there's where you're going, you're keeping your Hamiltonian constant or something. What goes on in the system, which is not changing the energy at all. So if you just have your energy detection, you can only see one state. But whatever goes on beyond that is about information, right? That's the information of the system is what's beyond the certain energy level. That's a very simplistic picture, but it sort of makes sense with and aligns with a lot of the kind of observed phenomena that you see, right? Like when you look at the expansion of a gas in a room, right? Like a typical example that even Stephen used when he was talking about entropy and things like that. Like naturally, the total energy of the gas is never going to change. I mean, it's a closed room, right? If you have a packet in one side and you suddenly release it, the energy contained as the kinetic energy or thermal energy of the gas is not going to change. But informationally, the system is clearly distinct from one point to the other. So that's kind of an interesting picture to bring up, because and it's one that I have been pondering about for some years now, because I never really wanted to dip my toes into notions of entropy or mutual information and things like that until I have a better grasp of sort of a static energy picture, and that's why I dedicate my research to like hypergraphs and things like that, and not yet to the like generative axioms that are behind that. But it's something interesting to keep in mind that information and energy are almost like orthogonal in some sense. They are almost like independent quantities that the one is kind of giving you a sort of landscape-like location, like energy, and information is giving you, once you are somewhere energetically or in some regime, it doesn't have to be one exact level, it tells you what you can do within that regime and that energy. It's very gross and sort of gross level and like a very very broad explanation, but it's kind of the concept.
Yeah, look, I hear,
dynamics laws basically, right? So you have the first law is your interplay between energy and entropy. Then the second is how the entropy is increased. I recently read some nice description of the laws of thermodynamics in terms of like the first law is about you can't win the game, right? The second law is you can't break even. The third law is that you can't even quit the game, right? And the zeroth law is also at least the scoring is fair.
Yeah.
what's that law that you mentioned? The name of that law?
That's just the first, second law of thermodynamics.
Oh, okay, first and second, yeah, okay.
Yeah.
Yeah, it's interesting. I think the angle that Stephen was taken, and I'm going to take my version of what I think he was saying, was that when you try to think of the energy in that closed system in that way that you've just mentioned now, Carlos, you cannot make those statements without accounting for the observer. And his refute of that setup is that in order to state that the gas is more concentrated here and less diffused there has to be somebody to be able to make that statement, and for there to be a claim that is a state that exists. So, and that the new state is something deliberate or not entropic. Because if you are completely agnostic with regards to that concentration of gas here and like a low concentration here could just be completely random. But there's something about the specific observer that's picking up on that not being random that makes it less entropic. So in a way, you building the observer into it. And that's where it becomes interesting, because is that observer within that closed system or outside of the closed system? And if they're outside of the closed system, it's not really a closed system anymore if there's a connection between energy and information, because effectively the information is leaking outside of the closed system. So that's where it becomes really interesting when you talk about these little devils inside the thing closing doors and whatever. And yeah, that's
right.
Yeah.
So I would like to address a question that is here in the chat. We can take a small science break. This quickly became scientific, which is great. That's what we do at the Institute. It's only natural. But there's a question here from Athelstan and also Elena, whom I know well, of course, is asking. They're asking about. So Athelstan's asked. Well, Aidan as well. Aidan Cook said, "What things should an undergrad start learning to eventually study things that the Institute does?" And then there's a couple follow-up saying, Elena also wants to know that, and also asks about how to navigate the YouTube channel. I'm going to answer that very quickly in a second. And then Athelstan follows up with, for when you get a question, can you go into specific advice for a pure maths undergrad? I've taken real and complex analysis, linear algebra, but not too much else. And then there's another one that says, what PhD should I pursue if I'm interested in foundations of maths physics? My interest in foundations is one of the reasons the Wolfram model piqued my interest. So I'm gonna, very briefly we can answer about the YouTube. So what I can say is that James and I are in the process of recovering accounts and doing some cleanup in the background. So bear with us. I mean, there's we would have wanted to have it much more presentable and much more tidy by now, but just bear with us. This is coming, and we will get it there in time. But for now, all the content is going to be on the live tab. So just come to the YouTube channel, go to the live tab, and you're going to see live streams recorded there, and you will have a title. They will always tell you what they are. We currently have 3 categories. So you will find community forums like this one today. You'll find live science live streams, which are just work sessions that we decide to put out. There might also be live coding, which same philosophy. And then we will have the explore and learn category, which we intend to alternate 1 week explore and learn and 1 week community forum. So these are much more sort of audience oriented live streams. Here and there we might also have what we call a fellow focus, where one of us decides that we've accumulated enough results and progress in one particular project, and we just want to showcase it and do a more sort of a one directional presentation where we show you all the cool stuff that we're doing. So all that stuff is going to be on the live tab of our YouTube channel. At the moment we don't have any more content there. I do expect that probably in the future there might be specific series of videos that we put out, and they're just videos that are in our YouTube channel and not so much live streams. But that's for that. Just I wanted to
the explore and learn concept is really to take a bit more of maybe a beginner friendly approach. So people that are joining for the first time this hypergraph revolution, or however you want to describe it, and then want to understand the concepts more from the perspective of somebody that hasn't been studying this stuff for a long time, or hasn't just been in the academic atmosphere that much. So it's really a lot of the time me just like trying to understand the concept to catch up to people that are making progress in this field.
Yeah. So then as a follow-up, exactly. Thanks for that, James, because as a follow-up, the most immediate answer to your question is during this explore and learn, and to an extent the life science and fellow focus one. So basically when we are talking about the science that we do at the Institute, we try to be quite approachable and quite accessible. Like at least I myself do emphasize a lot the accessibility of the stuff that we put out there, and being clear and explaining. I mean, after all, here at the Institute we are quite multidisciplinary ourselves, and we have different backgrounds and we have different training and different sensibilities and expertise. So we have to, this is not like me talking to colleagues in a university or to classmates in an undergrad where everyone is sort of attuned to the same language. We are making this effort to make it accessible, make it understandable, and in the process, of course, that's intellectually very rewarding, because you make it naturally better in some sense, and you make more progress that way. But if I were to answer that in terms of what to study, I mean, if I were pressed to give a very short answer, I would say do something that involves mathematics deeply and get familiar with machines that do automated processes. And by that I mean probably like code or something like that. I don't want to overemphasize like the importance of coding, because a lot of people would think, okay, what language, should I just Python or whatever? I personally never really coded that much. I learned C, C++, Python, Mathematica, R, like all these bits and pieces when I was doing my undergrad. And I've never considered myself a coder in some sense. But at some point you just realize, okay, these are just virtual machines that are doing sort of a little industry of their own to a lot of the things that I want to do. So just get used to that. But otherwise, what we do at the Institute, very broadly speaking, is science of a formal kind, right? So it's science that we can formalize in bits of code and we can computerize in some sense. And so I would always recommend that you study mathematics. So mathematics in the broadest sense possible. So go beyond what a mathematics teacher will tell you. Go beyond what physics major or physics undergrad is using to solve their mechanics problem, and try to understand that mathematics is about structure that is unchanged under different context, different application, different what we would say it's isomorphic, right? It's about isomorphism. So that means that regardless of whether you're looking at cells in a biological system that are doing their complicated things, or you're planning to send rockets to Mars, or you're trying to predict the financial market, like there might be structures that are totally unchanged between those frameworks, and to have a good vernacular of the structures that are common to all these domains. Personally, that's how I would define mathematics. I wouldn't even define mathematics as the particular tradition of thought that you can put all the mathematicians in a row in history. I would define mathematics more as that kind of common structure across disciplines. So you can very efficiently get that by going to the more traditional source of mathematics and learning algebra and learning combinatorics and learning graph theory, all those kinds of things. But beyond that,
can I just ask a quick question on that, because you just
Sure,
struck
please.
such an interesting point where you said it's like formalized science, and it feels like it's one of those analogies of like a mechanic who fixes other people's cars always drives a car that's like the least fixed up. So it's like, as a scientist, you try to formalize everything you're doing, but what you do is not necessarily that formalized. Like
That's
the
right.
way in which you do it is not a very formal process.
Oh yeah.
And just spending enough time around a lot of mathematicians recently, I've realized that it's and personally coming from like a computer software engineering world, and contrasting that to how you have these incredible towers of abstraction and systems that build upon each other and that have like schemas and type dependence and all this kind of stuff that really structures your ability to add on to stuff incrementally, and that speaks to the entire existence of what's gone before across different domains. And comparing that to how maths is done, it's like it's quite interesting. It's like it's an interesting contrast there. And somebody did mention Lean 4 in the chat, and that is a very interesting thing to pay attention to in how you can actually code up some maths and have your proofs proven.
Yes, and
independently.
I will mention, by the way, that as an institute excursion or an institute trip, I will be in Germany in July with one of the main developers and proposers of Lean. In this, there's a workshop on the formalization of mathematics, and so exactly on this topic, and so I'll be very happy to report afterwards, maybe later in the summer, in August or September, when we go back to maybe a post conference season and post summer kind of schedule, and go back to streaming, and tell you about that, because I think there's a lot of interesting avenues to go there. Now, to just react to some of the questions here. I just wanted to follow up on one of your comments. So yes, many people think of mathematics as they normally encounter it in their training. So when they go to school when they're kids, and what people think of mathematics typically, which is calculation or even accounting, or something that it's very much down to executing a process or executing some kind of systematic procedure. And definitely mathematics involves those. But I would say the activity of mathematics, the work of the mathematician, is highly non-like those, right? Like obviously you want to streamline those as much as possible to have them as your sort of building blocks. But it's almost like thinking that an architect is thinking about bricks, right? Like you don't think about, an architect is abstracting entirely the specifics of how a brick is going to be placed or how this joint is going to go in there. They are designing an entire building that needs to be resistant under this or that, or serve this or that other function. So that's more the mind of a mathematician. It's true that it's more like two subspecies of mathematician. There tends to be more problem solvers, and there tends to be more sort of theoreticians in some sense, that like to scope out and to explore, and others who like to really delve deep into one single direction. But mathematics is nonetheless an extremely creative endeavor. And one way I would like to characterize mathematics, I've said it in the past in this, I think this forum, exactly in the community fora of the institute, but I like to think of mathematics as the virtualization of industry, right? And by industry I mean this sharing of technology among humans, right? So when you go and you build a little a little tool in the countryside, early humans, and you say, oh look, this sharpened stick is good for taking meat this way and cooking it this other way, or whatever. And then someone else comes up with a particular stone shape that is good for cutting that meat or whatever that you're cooking. It's like and so when you actually go together to the reality of eating some meat or something, and you're manipulating literally these tools. Of course, you're bound by the laws of physics and the materiality of your interaction and so on. And so there's this interaction that is mediated by those. Now, it's obviously history of humanity shows you that as you accumulate on those encounters, you develop technology, you develop industry, which is this sort of networked technology, right? And so mathematics you can understand essentially as a virtualized, a mental imagined industry, right? Where you have all these tools and bits and pieces of technology. In this case, you might call it mental technology, right? And you're essentially just trying to iterate on them and add on top of each other and sort of share them and to see if they match. This if you had a very good industry for paper making, but you also have a very good industry for pigments and and coloring textiles and so on, then some people might think, oh, what if we could put the pigment on the paper and actually start writing? This is maybe two big industries that are initially unrelated, and someone comes up with the idea and they check physically if they can put ink on paper. Right, this seems like we can do some symbols here on this piece of papyrus or whatever. So mathematics is very similar to that. You have these realms of ideas, and you're constantly trying to have this constructs that are imagined. And the way that works is by communicating among mathematicians. There's very little that one can actually do and call it properly mathematics that is bound to a single mind. Right? That doesn't mean a single mind can imagine very far, and they can go very, very far in developing their technology, right? But the activity of mathematics is very much the act of sharing it and verifying that it actually interlocks and functions. And that's why I always like to remind people that the definition of mathematical truth is the consensus of the mathematical community around results, right? So obviously we might be in the position to change that now because of all the automated provers now, but it's important.
Yeah, it's very interesting. I think it kind of contrasts to engineering as a practice. Because as you mentioned with the architects, they're just thinking about the aesthetics and the look and feel of it. And my cousin, being an architect, mentioned once that what makes him a better architect than a lot of his competition was that he actually accounts for the bricks. So he when he draws the height of the ceiling, he knows that the number of bricks plus the grout in between is going to be a practical for that specific level of the ceiling. So when you get to actually building the house and there's the person laying the bricks, and then they're not stuck there being oh damn, this architect with his crazy visions of how this thing should look, now I have to cut these bricks in half. It actually just makes the whole process a lot more streamlined and efficient. And that's the concept of engineering. And somebody asked about computer science beyond just coding. And I think that's the kind of stuff that if you want to explore other ways of doing stuff and how to actually be more productive, is the engineering principles behind a lot of the computer science world, not just the theoretical concepts of this language has these features and these benefits, but how do you construct complex systems that can grow over time and not be burdened by the amount of technical debt that it has accumulated over time. And these are kind of the concepts of building on top of past works and allowing other people to collaborate with what you've built. Those are very profound ideas that I feel don't get taught at computer science classes a lot at university at all, because it's just about getting this project done and don't worry about the code. Sorry, some
that's essentially the difference between coding and software engineering. It's one way, essentially, when people do some challenges, just make some algorithm much as fast, run as fast as possible. It's in the small amount of code and all that. It's this coding, right? This is the this trick to actually write to explain the computer what to do. But the software engineering is actually how you can build more complicated systems on top of other people's work and
it's code.
And all that.
Exactly, it's coding after time that's recursive, because you have to go back and actually understood what you wrote the first time and have other people work with it. So how do you do maths recursively where you have to read your own stuff later on, and collaboratively where other people have to understand what you're doing? So applying more of an engineering practice to mathematics makes sounds useful to me.
In some sense, there's one could even pose the thought that the only distinction between software engineering and mathematical research is the fact that you code either on silicon or on human brains or something, but because the analogy is very, very, very powerful. like the fact that you like to think of mathematical theories as software running on similar hardware, and that's why we sort of all understand, what a set is and what a vector space is, and all these kinds of definitions that are very almost self-selected. Like humans understand them well, and that's why we use them. So it's almost like your computers, they understand whatever the machine code or whatever, that down to like Boolean operations and all that stuff, and on top of that you build. There's a very strong analogy there, and it's very interesting. I mean, I feel very lucky in some sense that to be in a generation or set of generations that are experiencing what might be a transition from mostly relying on this distributed brain software, right? This idea of culturally distributed ideas that we imagine to be exact but can't really verify externally, to a situation where we are building the environment, meaning our digital technologies and our sort of informational technologies around us, that might just do that for us instead of it's an interesting.
Yeah, and it brings up an interesting question.
Just a quick comment that you can even call this, when people prove something in Lean 4 or whatever, they can call it mathematical engineering instead. That's like
And what's interesting with the development of Lean is it's becoming more like a conventional programming language, and it won't be out of reality to think that you could just create computer programs in a mathematically provable way in the future. You could. I'm learning all kinds of stuff.
I might be. I honestly think that there is no mathematics was programming before programming in some sense, right? Like before you had computers, like mathematics was. There were several instantiations of programming that existed before digital computers, and I'm going all the way back to like Leibniz, or even like some very old computers, like mechanical computers and things like that, like legal systems, accounting systems, all these kinds of things. They were even like libraries, sorting systems, just having archives and things like that have their own taggings. I mean, if you think about it, that's exactly what your databases are, and like all the a lot of algorithms that you do in a database nowadays are like what the monks were doing in the monastery to keep track of all the transcripts that they were doing. So it's almost like the analogy is almost full. You just change the timescales and you change the substrate of where the information is kept, and it's almost complete, right?
Well, although it does bring up some interesting questions, because what will be the most difficult thing to transcribe into digital for humans? Like, what are the things that we do that's uniquely suited to our hardware, and vice versa? What are the things that machine learning?
Yeah.
Let me ask both sides of the question, right? So there's the human hardware advantage, but then there's the machine hardware advantage, where you could imagine how artificial intelligence could come up with new types of mathematics that would be impossible for us to even comprehend, and how would we be able to operate in that world?
Yeah, as a meta comment before we address these questions, which are very interesting, I'm not forgetting about the questions that we have on the chat, but as a meta comment, it's funny that we get to this kind of question very consistently in these live streams. Probably Nick and Richard remember that this idea of sort of like the xenomathematics and what kind of mathematics is the AI going to be doing, and it's a very recursive theme. I love it, so I'm all for it. So I'm very happy to. So maybe before let's put a pin on that question, because I think we can spend some quality time there. But let me just address Athelstan's question here. They say, how do you all implement your ideas that you learn when reading papers, textbooks, or watching conferences? Do the ideas sort of marinate in your mind, which eventually feed into your own new ideas? And I think they follow up when did you all start feeling comfortable that your new idea would be useful, in quotation marks, to the community? How did you find that would be useful for your own niche? So I can speak from experience, knowing. So my research ethos personally is to be very careful that you are addressing a question that is not well understood generally. So that is sort of a study phase where you go and study what others have understood about your question. So how long you spend in that phase, it's going to change from person to person. I think it's good practice to not get lost in that, because when you're learning for the first time and you're an undergrad, there's virtually the entirety of human knowledge that is unknown to you, and it's very important that you don't think, oh, but if I want to know a bit about this, I should also know a bit about that, and then you get completely bogged down and you don't make progress. So it's very good to sort of virtualize that process and imagine, okay, I'm just going to imagine that all the knowledge in the universe is the first chapter of this calculus book, and then you take it in. And then you say, okay, how do I solve this optimization problem? I only know about derivatives. You might come up with the idea that, if you try to find critical points, that might be a way to solve optimization problems. So those kinds of exercises are super important to learn. And in some sense, that's what research is all about. Like at all stages of expertise and level, so to speak, that's what you always do. You always say, okay, I'm going to assume that I have this at my disposal, and now I'm going to try to go to some new place that I don't really know. So you always have to make some kind of judgment on, I'm just going to limit myself to these tools. And I would always personally try to make sure that I have quite a bit of certainty that something is not well understood, and there is some open questions. I mean, in mathematics, this is very classic behavior where, there are literally open questions, like propositions that are not known to be either provable or true or false or whatever. So in that case, it's very simple. In other cases, it's a bit more, blurry and a little more intuitive. But I would always recommend just check that it is indeed something that is not well understood. And then I think the idea is that you set a very concrete goal and try to go for it. And if you don't, if you get very stuck, you don't just die in the process, right? Like you don't just burn yourself with, I need to really finish this thing. But always keep repeating the same process. You don't think that this problem is your life, and if you don't get it, it's over. But also when you take a new project or a new problem, you need to really kind of tunnel vision into it a little bit. So I think it's very important to kind of leave up the fantasy that only this problem is relevant in the world, for entertain that idea for a few weeks or months or whatever, and then you try to move on, and then you try to sort of integrate it in a larger context and things like that. So yeah.
So it's like a very human type thing, I struggle with studying just raw textbook type knowledge, and the only way I managed to do it was to set up my motivation literally every time before I even open the book, and say okay, before I start reading or getting into it, what is the motivation for why I'm even doing this in the first place? And having that goal, even if it's a far-fetched abstract goal, helps you structure your knowledge and your learnings around a specific narrative thread that you can always go back and anchor to. So it helps you remember things that way as well. It's okay, what was it that I had to remember with regards to this goal? Oh yeah, I started here and then I did this and then I read this. Okay, now I remember, because it's got this associative type structure. So setting up the motivation is very important, and then having timelines is important too. So the practical constraints, so you don't go wandering off too far into the deep end of something too abstract, combined with a motivating goal. So those are very useful.
Yeah. Normally when you get people, the most validation that you could ever get for a research question is when you ask people who have dedicated a fair amount of time and energy to understanding some realm of ideas where you think your problem is phrased, and you ask the question and you get mostly perplexed answers. You don't get either oh, that's an interesting, or you don't get a direct answer, oh yes, this is such and such and such. If you get indifference, I would say that's non-data. But if you get just kind of a bit of a perplexed answer of okay, interesting, I don't know, maybe, but isn't that right? And then they say an obvious thing and you say, no, but to point this out and say, actually, that's right. So when this happens, it doesn't matter if it's mathematics, if it's other things, you're usually on the right track, I would say. That's probably a good sign that you are pointing at something that is, that doesn't mean that it is valuable in some ulterior sense, ulterior sense, but it does mean that it's a valid research question and something that, if resolved, will add to the aggregate knowledge of humanity in some sense, right? But yeah, so they are asking for the AI versus human mathematics back. So I guess, James, you should restate your question and provoke
Okay,
us.
so let's pick up from what Richard commented on there. You mentioned
Did
inference.
Yes, please. No, Richard, please go ahead.
I hadn't quite finished. Yeah, I had some points, but do you want to restate the question and then I'll.
Yeah. So what is it that is uniquely advantageous to the human hardware versus what is advantageous and potentially untranslatable in the machine world to humans?
Yeah. So, I mean, just backing up a tiny bit, we were talking previously about the connections between like mathematics and programming. And one place where that happens, specifically mathematical proofs and programs, is that Curry-Howard isomorphism, or also known as propositions as types. And you had also touched on sort of, like verifying programs or doing it in a more formal way. And it was Tony Hoare who did that in this Hoare logic thing, which is like a predicate logic for reasoning about sort of preconditions and postconditions for various steps within a program. And then in terms of like the new theorems that AI would come up with, we did explore that a little bit on the last blog project, but the only work I've really seen on this is by Alan Bundy, this automated theorem exploration work, where they're able to have the system kind of discover very complex proofs in like really tricky domains just by itself, which is quite impressive that it's able to kind of recover stuff that humans found. But usually these domains are quite kind of formal. So another thing we had encountered was that this translation between formal and informal statements. So you could take like an informal statement and sort of formalize it, or even go in the reverse. And I think the power humans have is really to make these kind of intuitive leaps. And some argue that these things are actually non-computational. That's up for debate. But perhaps it's the case that, when we start training these multimodal models, not just language models, but models that are seeing, hearing, reading text, that they would be sort of absorb more concepts that human beings work with and can then apply them. Sometimes I believe, in a way, I don't know because I have no direct proof of this, but these people who was the guy who did Fermat's last theorem and so on?
Andrew Wiles?
Forget his name. Yeah. Like I've watched a few documentaries where they speak about these kind of flashes of insight, or like, they almost gave up and suddenly something came to them and they went back and wrote it out, and he couldn't lay the paper on his desk, and he had to walk away and come back to be really sure that it was real, and he checked it. And
he discusses it quite nicely in an example where he was trying to understand some Arab language, and he sat down with the language itself, some kind of like Greek or Latin or something, and he was trying to work out like one letter at a time, and like he was really racking his brain, like he couldn't do it, and he just gave up. It's like, this is too difficult, and walked away, took like a long stroll, came back, and then he could read the entire thing. So there was something about this synthesis and this maybe like subconscious synthesizing of ideas that are not formalized even to our own like prefrontal logical cortex, something's happening there. And if you believe some of the Penrose stuff, it's potentially even like a quantum type thing that's happening with the microtubules and neurons and that type of stuff.
Yeah, his argument is that mathematical kind of reasoning or whatever has like these non-computational steps in them, but who knows? I mean, just the way in which we're able to sort of generalize and abstract or whatever seems to be quite kind of out with the reach of sort of current computational technology, but we don't know. We were surprised by, the scaling phenomenon that we've seen with LLMs. We don't know if it will continue. Some people are seeing that it's not continuing as they thought, but I think the AI will be useful, but it's not going to perform magic, and that's kind of an obvious.
But at what point would it seem like magic? I think that was the flip side of the coin. And I haven't looked too much into it, but there's been these claims about large language models or just machine learning in general figuring out novel mathematics that we don't quite understand. And
there was already examples of that where, say, automated proofs were generated that were completely incomprehensible, and people had to go in and look. I mean, how would an AI sort of develop new notation or even new terminology, or in fact,
Yeah, with Wolfram language, I think even ChatGPT will invent function names that Wolfram, the company, have imported because they were good. Like, oh, this function name is a really good name for that functionality, and maybe we should rename our function because this is better. But I think it will always be like a teamwork. You know, AI will be our sort of sidekick. Maybe.
Yeah, I want to pick up that thought because I've mentioned several times the way I think of AIs and sort of the future of mathematics and the future of science in this landscape. And I think what's useful to think about is what I usually call the cognitive landscape, and where you have different entities that behave in ways that we describe broadly as cognitive or broadly as computational. I mean, the two kind of blur into each other, and I don't want to get into the specifics of that, but we intuitively understand what we mean by this. I mean, obviously humans are examples of that, but a calculator is an example of that. A mouse that you see running in the forest, this is an example of that. A bird flying around is an example of that. And so we, the simpler the physical system, the simpler the machine that you choose as a tool that you choose to interact with, the further away from this cognitiveness you would perceive it to be. But the more you infuse it with systems that replicate either structurally or just behaviorally in terms of input-output, what we familiarly understand as cognitive, as others, right? Like as similar others, then the more it would resemble like AI. So my point here is that the game for us, until we transcend into the matrix and we become one with whatever silicon hybrid systems, and your human intuitive experience is completely distorted and changed, until that day comes, or when that day comes or whatever, your mathematical life is always going to be essentially the same. You're always going to be interacting with your hands and your eyes, and you're going to be looking at patterns, visual patterns. You're going to be looking at things that change with time and so on. So you can't really escape that. So whatever we decide to invent with these systems, with these AIs, language models, with other generative models, whatever, it's essentially going to be like creating some species of little aliens that their only prerequisite is that they have some interface with us, right? Like the fact that ChatGPT is this very complicated thing, this very large transformer, whatever. The point is that it has a chat interface, which is something that humans were already very used to because we were chatting with each other, on phones or whatever. So that interface was a human band of connection. So as long as you have a system that has those kind of interfaces with humans, it doesn't really matter what goes behind it, because Mathematica has been in this business for a while. Like Wolfram Alpha has been in this business with like computational language, computational intelligence, instead of just purely sort of more stochastic or more statistical intelligence. And these all these systems, to me, they all kind of feel the same. Obviously, they are more or less powerful or more or less efficient for different tasks or different functions, but they kind of all serve a very similar process. Like the way I would use a calculator. Like, the kinds of things I can compute with a calculator are completely beyond my capabilities, and no one was like losing their minds over the fact that we all had calculators when we went to school.
I don't know. Back in the day, maybe the first invention of the calculator made a few people worried.
Sure, in terms of, I'm talking about the losing their minds in terms of more philosophically or intellectually, not so much like, obviously economically they're very, very high risks here. There's a big disruption probably that's going to happen at some point and things like that. But I mean purely at the level of the future mathematics, which was your question, and what makes the more AI-like systems and the more human-like systems better or worse. I think it's all about your subjective experience of that process, and you're always going to. These systems, like an alien race that are just like completely structurally different from us, they're going to conceive of things that are like literally unconceivable to you, but not because they are like bigger or larger or anything, but just because they are in a different framework, different substrate or whatnot. And so something that is computational has access to like digital hardware, for example. Digital hardware is extremely good for bookkeeping, right? Something that is not so good in sort of soft hardware, in the sort of the neural tissue. Neural tissue is not so good for bookkeeping, but digital hardware is super good for bookkeeping. So you could imagine AI is coming up with mathematical theories that in which the kinds of operations that they consider are very large, right? Like the number of arguments in each of operation is super large. The kind of axioms they satisfy, the kind of laws that they satisfy are very baroque for our, if we were to write them out, they might have like hundreds of characters and hundreds of like very deep trees of expressions and so on. And as long as they're interfaced with those expressions is efficient as it is with their language processing or their images processing or whatever, they are going to run off and they're going to develop their mathematics about those things. But the question is, will they be able to communicate to us what they are learning about it? Because it's not only like finding true or false statements and like proving things, right, about those things. It's about them telling us what those things are doing in a way that is useful for us, right? It even boils down to that, right?
It's an interesting idea because how do we trust that they're not hallucinating in some high degree of abstraction that we would struggle to comprehend at some point? Because, I mean, even in Lean, there's a very imperative or declarative statement with regards to like utilization of axiom of choice and these kinds of things. So who's to say that there's not new axioms that need to be picked at those higher levels of mathematics that would potentially show contradiction at our scale?
Well,
and then
my answer would be, how would you make sure that Andrew Wiles was not hallucinating when proving Fermat's last theorem, right? Like that's to me the answer is the same for those questions. Like it doesn't make a difference if it's a computer or if it's a human. I mean, to me, humans and computers are essentially as black boxy. Like by now that we've got to a situation where you show me a computer.
I think the difference might be is like if it's a human, then at some point another human or a group of humans could get there. That's
Wiles
kind of the
did have
difference.
A mistake in his proof, right? When he first published it, he had to correct. So
yeah.
I think there's this level of certainty you have is like a human came up with it. You know what I mean? It's like. And whether it's right or wrong is not really the question. It's more a case of like, would we be able to validate it? Like, could we get there and then disprove it or not disprove it? That's kind of like, is it possible to disprove or not disprove it? But if some kind of like very advanced machine mathematics gets developed that's beyond the capacity for us to even reason about, that's the question. It's like, would that be possible? Like, would it be possible?
But you could have a dialogue with the thing, like you could speak to Andrew Wiles and ask him and whatever. So yeah, this dialogue interface would allow us to sort of pick up on certain points and ask the thing to elaborate or whatever, show its reasoning.
I want to understand your question exactly, James. So you're saying whether it is possible at all that there is a kind of mathematics that is inconceivable to us, and only the machines will speak that language, and we won't know about it. Is this what you mean?
There's different degrees of conceivability. There's the ability to conceive it like right now, to be able to conceptually hold it in my mind, which has limited bandwidth, and this is observational boundedness and that kind of thing. But there's also the ability to possibly comprehend it, and what's outside of that. So so no matter how many humans work on this for all of eternity, it's not something human hardware like loadable.
Yeah. I think I get your question. I think at this level, I always resort to the fact that understanding or reasoning and thinking, proving mathematically, it's for a human is, although we virtualize it as I said, as some kind of mental industry, it always is bound to some kind of motivations, right? It's always bound. I don't mean to say that you need to be in the real world or something like that, but it's actually bound to. You set yourself a question. You set yourself for a confirmation of something, and then you go check that something, right? So, if you, by definition, say there are things that humans are not able to express because the hardware doesn't allow for the expressivity of this other hardware, which for whatever reason, for architectural reasons, I'm sure that some mathematicians will tell you that no, that actually because of the universality of computation, you can actually always express. It's just a matter of size. I mean, I am a bit agnostic about this. I'm not sure that the formal notion of computational universality actually lets you make that kind of assertion. But the thing is, you can. I mean, a human will always need motivation for a question, right? And even if the motivation is sort of self-referential, say, well, I want to know why this thing is this way, like it's just referring like to parts of the same abstract mental entity. You always have this directionality. So as long as you can formulate those, so for example, if an AI, this AI, let's call it whatever, the AI conclave of mathematical AI conclave comes up with all these theories, and they design a graphic language for it that's just 2D, that you can just project down into D, and you can see some one-to-one correspondence of like statements in that language with some diagrams. So to us, they look like this completely baroque, complicated, intricate patterns and diagrams, right? Like at first we have no intuition, but because we can see them and we can engage with them and take them in as a human, then we might think, okay, let's start to analyze them. So this is very much like, you find an old lost language in archaeology, right? And then you say, okay, how do we reverse engineer it? I mean, in that case, it's easier because mostly you're going to assume that humans did it, although some people have very crazy ideas about that. But if you assume the humans did it, you're mostly playing this idea of sort of like reverse engineering your own mind, like what would I have done if blah, blah, blah. In this case, you can't do that, but you can nonetheless try to decipher and try to like make sense of things. And that's the worst case scenario, when you only have something that is projected down to you. The best case scenario, you have an actual conversation with the entity, and you have a intuitive understanding that the entity is exploring a formal world of possibilities that is similar to the one that you are exploring. Just maybe doing it much faster, maybe doing it by means that are very unintuitive to you, which is almost like when the analogy of navigation and physical space navigation, right? If you're just used to walking and you never saw like a bird or anything, you never see anything fly, right? Navigation on a landscape is always based on like landmarks here and there, and like mostly sort of a path-based navigation, right? And sort of sequential navigation. Like the moment you get on a hot air balloon or something, or you just fly over, or you see it from a high hill, suddenly your cognition changes. It's like, wait, I can organize with a single picture, I can organize directions and I can organize locations and so on. So this is the kind of thing that might be happening, that we might be just, the moles in the ground, just making our way like in the underground, and the AIs might be the birds of prey that are just flying above, right? But if we are inhabiting the same ecosystem, we are inhabiting the same sort of setup, there's still a chance that we can have a conversation, right? Because the mole can be picked up and then they can see, right, this is where I was, right? But yeah, it's, but obviously it's very fun to imagine what they, in sort of a sci-fi way, like what they would be doing if they just are left unconnected to humans, right? Like if you just go off and they never have to report back to humans. Like it's always fun to imagine. It's like, oh yeah, they imagine what they would be doing, like whatever. It's very.
It keeps reminding me of these. It's an anime called.
Oh,
Bland.
you're going to talk about the Tachikoma? Oh no, sorry. You have a different example. Okay, you give yours and I'll give mine.
So in Bland, in Bland, basically the concept is that Tokyo as a city becomes so advanced, as far into the future, that the city built itself. And it basically runs wild, and it just ends up continuously building, and all these robots and like massive machines just like carry on. But it ends up becoming more like a desert because it's just the city itself. So these roads get developed for no reason other than because it's a road, and all these like various things. And then there's some human survivors in this kind of like post-apocalyptic world, and they are trying to like steal some resources here and like try to find a way to survive in this never ending growing ecosystem. So it keeps bringing back those kind of memories. It's like the AIs have just run wild, and they continue to build this space that is supposed to be for humans, but the humans have been relegated to this like small little survivalist class.
The other anime example is in Ghost in the Shell. They have this standalone complex series, and there's like a kind of interlude episode where the Tachikoma, which are these little robots, and they have like a little hive mind. But in one episode, they get like the wrong oil, so it's like making them drunk or something. And then they start having this philosophical monologue, which gets like really interesting. And they're like, but it's all the one brain, but it, you know, it doesn't know that it's talking to itself, so it's having this kind of conversation. Anyway,
By the way,
it's one to watch out for.
Yeah, this reminded me of a very short movie on YouTube called Solstice 5. I'm just gonna share the link on. Does it sound familiar, James?
Yeah, I watched it. It's pretty cool.
Ah, it's super cool. So I'm just gonna share it. Oh, where's it? Oh, here. I'm just gonna share it on the chat for everyone's benefit. So it's a pretty cool project, but it's a 10-minute world building exercise essentially. And it's very similar to this idea of a system that just keeps on going. And you know what I like to think about those. You know, I love your example that says that Tokyo seems to just keep on growing, and you know, it makes roads just because it's a road. And I love it because that's exactly how, like, maybe a neuron sees neurons growing around them. It's like, oh, those dendrites are just going everywhere just because they can, right? Like if you sit in a neuron and just see the dendrites like going back and forth, it's like, okay, these dendrites are just moving around because they can. Like there's no, and then suddenly you have yourself being conscious and doing all this crazy stuff that we do, and you know, as an emergent sort of a process there. And I think it's very interesting. Like for a while, I was thinking of this concept of what I call the cognitive landscape or the cognitive continuum, or like, you know, we are all part of the same universe apparently, and apparently as far as we can tell, we are all under the same laws of physics, and you know, it seems that the universe is quite consistent with itself.
That's
right?
that's one direction of theories. There are other theories.
There are others for sure, but
Yeah.
I mean, I will have to be very strongly convinced that the universe is somehow not keeping track of itself, because so far it seems to be very good at keeping track of itself.
According to you, based on your
sure.
perception, right?
Well, my perception and everyone else's, I think every human, at least in the physics community. So the point is that because it seems to be the case, and it seems that a lot of the matter that stuff is made of is not super relevant, but what is really relevant is more like the structure that it configures itself into. It's always fun to think about where are the kind of minds that are out there, right? Like, obviously we know what it feels like to be a Homo sapiens brain emerging, body emerging mind, because that's what we're doing now. So it's fun to think about, okay, what other kinds of minds are, and I don't mean animals. Obviously, animals in some capacity, or even plants, maybe to some capacity, they have like minds of their own, and like fungi networks and things like that, which are kind of like the obvious examples. But I have a fun time just coming up with examples of where would be like things that are developing minds in some sense, where you can only explain behavior when you are the thing doing things in a setting. And people have examples of. They have speculated about, entire ecosystems, forests, turbulence in stars, planetary clouds that have basically mediate this idea exactly of energy or like the free energy, and like the sort of the energy flux through a system, and how if you remain in an energy band, what goes beyond that is information and the flux of information. So to me, it's always fun to try and sort of daydream of, what is the internet thinking right now? Like, that thing is extremely complex and extremely interconnected. And, is it thinking something? Does it have a ham of its own? Does it have a self of its own somehow? And, these are the fun questions for me. Like, I like to entertain them for fun. I don't have very insightful thoughts or anything scientifically, but
there's a few interesting things there. I've been thinking about these ideas quite a bit, and there's an interesting concept that potentially it could be related to the second law of thermodynamics in terms of like expansion. There's another interesting concept in terms of entropy bounds. So if something is too simple, like mentioned earlier, you wouldn't be able to talk to it because it doesn't have the cognitive ability. But what's the other end of that spectrum is something that's too complex. It's so complex or not even complex, that's not the right word. It's like too entropic that there's so much going on that you also cannot have a conversation. from your computationally bounded observer's perspective. So it kind of feels like there's this like perfect warmth, or like kind of like this happy space where dynamical interactions can happen, and all of complexity exists there between those bounds. And there's different ways you can analyze those questions. So probably this is the reason why science and research and the type of stuff we're doing exists. Is like you can ponder these things, but there's actually things you can do to structure conversations around it, to ponder it in more formalized ways. Yeah,
Definitely.
Okay, should we announce some?
Yeah, let's move on to some announcements. I wanted to maybe so we don't have Xerxes here today with us, but I think it's relevant to bring up that the Wolfram Summer School is now online, and I think people can register. So I think if you follow the usual link where this thing is hosted, I don't know if you just shared it, but I'll share it here. So there's one thing that is coming up. I imagine Nick will be there. I will be there. By there I mean virtually, because I have to attend virtually this time as well. I think Nick as well. But yeah, that's something that's coming up, and registration or application process is open. Yeah.
Great. Of course, you're gonna share your screen, and we can show them the poster that we've been working on.
How do you want to share that? Should I? Maybe you can share the screen. I mean, I don't want to mess up the.
Okay, give me a second. I'll bring it up. Yeah. So.
Yeah, put it somewhere that they can be seen, and then we can make an announcement. So this is a follow-up from the one and only event that we managed to run last year, and so we are doing a repeat.
Okay, share my screen. You're gonna see a picture of a animal first, and then I'll bring it in here.
Mm-hmm.
Okay. Ta-da!
Nice.
Hypermatrix workshop number 2.
Yeah, so we are revisiting this event. Last year we had a very nice experience when we invited some computer scientists, mathematicians, some people from algebra, some people from physics, that they were working on this idea of extending matrix algebra. So basically, every single language model that we have nowadays, all these machine learning processes, they involve matrix multiplication in a very fundamental way, meaning that many steps involve doing that operation. So this workshop last year was themed around the idea that, okay, what are the possibilities here? I mean, we're doing matrix multiplication because we know how to do it, and it's extremely powerful for certain applications, and we learn it in school, and there are very powerful algorithms to make it efficiently and so on. But what else can we do, right? Can you maybe multiply matrices in a different way? We know we can, and you learn about those products sometimes in high school. Why don't we use them more? Should we use something else? What happens when we take instead of matrices, we take what people mostly incorrectly call tensors. So meaning, higher dimensional matrices where you arrange your scalars in cubes and hypercubes and so on. And basically lists of scalars. What is the natural algebra for those things? Is it all reducible to matrix multiplication? The working assumption, if not conscious, definitely unconscious in the vast majority of the machine learning community, is that effectively everything is reducible to matrix multiplication by throwing some nonlinearities in that structure. I think we have very strong evidence that that's not the case. That there's actually very rich and complicated structure in higher, what we call higher arity operations of these objects. And so this workshop is last year was primed by this kind of question, and this year we're going to have a on-site leg for it. So if you happen to be near Paris and you want to show up, drop us a note, and we'll make it happen. We're going to be hosted by the Center for Condensed Matter in Paris Sorbonne. So we're gonna have I'm gonna be there in person in location, but we're gonna have the event running virtually, hosted by the Wolfram Institute. So it's a joint effort between some local Paris universities and the Wolfram Institute, and we are gonna have 3 days where you can see contributions in more sort of a theoretical physics kind of angle, where more traditional tensor analysis, more common to physicists, more well-known to physicists, is the focus. The second day we'll have a hypergraph focus day, where we'll have some people talking about hypergraph rewriting from the categorical point of view. We'll have some higher order network analysis from using hypergraph methods. We'll have some data science with hypergraph techniques. And then the final day, we will talk about the higher arity algebras of these hypermatrices proper. So I will be running it with, I will speaking myself with Josh Rochelle, which is another researcher in this field, and one that it's been occupying most of my time and in the way of my research. So yeah, everyone is welcome. We'll make the appropriate announcements on Discord, and you will get notifications. So for now, if you are on the Wolfram Discord, Wolfram Institute Discord, you're in the right place. Otherwise, make sure to join, and keep an eye out for announcements. And yes, everything will be recorded, Elena. So if anyone, so everything will be live streamed like this live stream. So just come to the same venue here during those days, and we will have the talks and the discussions live streamed here and open to everyone.
Awesome. Interesting question there by Aidan. I'm going to stop sharing this, and then we can maybe discuss that as a closing thought. And then, yeah.
Yep. Aidan, there's a question, says, why is it that so many of the Institute's research areas can be formulated in terms of rewrite systems? Are they the most natural multi-computational system? Answer to the second question, I mean, maybe Nick and Richard can give you their opinion, but in my opinion, yes, they are the most natural multi-computational system. It's hard to imagine a multi-computational system that is not rewriting based if it's not stochastic in some sense. So the choice is kind of binary there. I mean, you have a stochastic system or you have a rewriting system. It's hard to imagine something that is not one of those two. So if you want to do deterministic computation, okay, I mean, probably Nick agrees with me that that's probably a particular case of stochastic, right?
Stochastic. What do you mean actually? Repeat.
Yeah.
Stochastic.
Yeah. So if you have something that, if you have states and you want to multi-evolve them, like you want to alter them somehow in a multi-way system, right? So you're branching out and you're following different paths and so on. It's difficult to imagine a system that either explicitly rewrites or just takes some stochastic process and some kind of. It's difficult to imagine something that is not those two, right? That's what I meant. And that quantum would be an example of the probabilistic kind of.
Yeah, basically you have to at least have some ambiguity of how your action applies. It's like as soon as you have some way of iterating your system over and over, like as soon as you have some ambiguity, then it can be multi-computational. And just rewriting is just maybe probably the most natural way of having like patterns overlap, multiple ways of applying the rewrite.
Exactly.
So that's why.
So would you agree that quantum would fit under a classification of the stochastic version of that, or is even a rewriting system a type of stochastic process?
Well, actually, still kind of have two versions of where the stochasticity in quantum theory comes from. If you just have a arbitrary multi-computational one, right? If you just hand me the multi-computational system in terms of rewriting, right?
Yeah.
Where the stochasticity comes that you interpret as probabilities later in the quantum case, right? It can either be interpreted as some kind of actual statistics over whatever system you're rewriting, or it actually be interpreted as paths
Yeah.
or like branching and merging. And
Yeah.
the statistic, it's either dynamical statistics or statical, like the static statistics of a state.
Yeah,
And
exactly,
like two
exactly. Yeah, exactly. That's a very good point, Nick. And I wanted to emphasize that because it seems that the fundamental laws of physics that we have discovered so far, they seem to be conservative, meaning they are essentially time reversible. The fundamental dynamics that are assumed in the classical presentation of these models, for example, Schrodinger's equation or, Hamilton's equation for your favorite system, classical quantum, doesn't matter. These equations they are ODEs, right? Like they are deterministic. If you have mathematically a state, they will predict a unique future state, right? So you have to, you have then two choices. If you're thinking in terms of more physical systems, you need to either introduce uncertainty, which classical or quantum doesn't matter that much. I mean, uncertainty is always going to be there. But I mean, if it's quantum, it has its own flavor. If it's classical, it has its own flavor, but doesn't matter. It's uncertainty nonetheless. And uncertainty is going to lead to branching, right? Because it's going to lead to, you're not sure what in a set of possible dynamics your system is going to take on. And that's the kind of physical interpretation. The more formal interpretation, the more abstract interpretation of the rewriting kind of perspective, that's what the question was asking, why rewriting systems essentially. So rewriting, there's one motivation for rewriting that makes it the most important kind of systems to study right now in the context of the research that we do at the Institute. And that is that everything we've been talking about today in terms of what mathematics is and whether, like coding and software engineering is kind of a progression of mathematics when your pen and paper is replaced by some machines that do some automated processes and so on, and how in the history of mathematics, people have shared ideas on how we check what's true and automated theorem provers and what AIs will dream up and so on. All this conversation is bound by the fact that in practice, mathematics is this communicational process where you need to use symbols to encode meaning of some kind, and then you those symbols. The reason we call them mathematical instead of just whatever squiggles or drawings or whatever is that they are infused with some life of their own, right? And this life of their own is what I meant by this mental industry or these mental machines, right? It's like literally they get to operate in some formal way, in some imagined mental way. And that operation, in the vast majority of cases, when you look at what the kind of mathematics we do, is rewriting. It's literal symbol rewriting, meaning you have an expression, you operate on the expression, and then the expression changes. You have an expression, you operate on the expression changes. And when you learn basic arithmetic for the first time and you're told parentheses, multiplication takes priority over parentheses over addition, those kinds of things. Those are exactly rewrite rules. I mean, you never call them that, but those are exactly rewrite rules. They are telling you when you see a bracket, you can only collapse it if you first compose what's inside, and then you do the thing that's outside and things like that, right? So rewriting is at the very core of how mathematics is practiced, right? And it depends on your philosophy, it depends on your favorite formalization framework, it depends on whether you think like hardcore, set theories that, you believe at the bedrock of set theory is where everything is built, or you have a much more diagrammatic approach where, you're a categorical kind of thinker and you're thinking more in terms maybe of homotopy types, or, it doesn't really matter, because at the end of the day, if you practice mathematics, you're going to engage in this kind of ethos. You're going to engage in this kind of process in which you put your thoughts to symbols. Symbols could be words, by the way. They don't have to be written somewhere explicitly. But these symbols have this sort of recursive nature that they what identity is. What the same thing is the same thing. That, and you also know when something has changed as a result, right? So in that process, it's how mathematics kind of is built. So, in my opinion, that's why rewriting is extremely fundamental. Now, some people, maybe Stephen himself would say, we have evidence that reality is fundamentally about rewriting. I don't know about that. I personally don't have a strong intuition about that claim. But what I do know for certain is that both the purely formal aspect of rewriting, meaning it kind of captures the essence of mathematical practice, beyond any more technical statements about it, and the fact that it gives you the most natural example of deterministic rewrite systems. By deterministic, I mean that once you know how a rule applies, that rule applies in exactly one way. Then you then make this extra step to physical systems, and you say, well, how does reality operate? We have all these laws that we've inferred with calculus and like Hamilton's equations and Schrodinger's equations, all these kinds of things. And then you realize, wait, these rewrite systems seem to be having a behavior that is very analogous to that. Because they have this idea that once you have a state and you have some defined rewrite rules on that state, then that state evolves. The evolution might be linear, meaning there's one single thread of changes that are recursively happening, or they might be spreading. And you know, our computing has been mostly based around this idea of a single path computing, right? A single path where you have actions that are more or less always defined. And that's almost what an algorithm is, if you think about it. Like it can be parallelized, but in every chunk, it's mostly one single thread of actions, because we are sequential beings and we live in time and we understand that. But when you think about something like biology or evolution, or even cognition in neural networks, and both biological and artificial, like you realize that computation in this sense, or cognition more generally, happens in distributed non-sequential ways most of the time, right? Where causality is a rich kind of intermediate phenomenon, and it's not just one sequence of things. That sequence of things is more like a abstracted subjective experience of one particular part of it. So anyway, so then it has this beautiful translation, right? Like the abstract reason why we think rewriting, or I personally think rewriting systems are so powerful, has this then natural translation into the actual world of what we observe are the most general processes, and for example evolution and cognition and so on. So to me it feels like if you try to model your mathematics more against this kind of multi-way, multi-branching kind of phenomena, instead of being obsessed with the syllogism structure, the kind of I am arguing in the agora in classic Greek times, and then just trying to make my argument perfectly follow from my premises. I mean, that's powerful, that's great, but that's not the end of the story. And so we are trying to sort of expand that to be inspired by more general systems like evolution, or like that's why we call them cellular automata, because they're kind of like cells that are doing their thing. And so anyway, that would be my answer to that. I would love to hear Richard's and Nick's thoughts on this question, and obviously yours as well, James.
Richard.
Yeah, just thinking there. I mean, before Wolfram, the places where I'd seen non-determinism were things like NFA to DFA. So that's like a very, there's multi-computational aspects, but not really kind of, Can
you break down that acronym for us? Sorry.
Mm-hmm, yeah.
All right, so and this is all very kind of like practically motivated. So when you're dealing with regular expressions, when you're composing these operations, you end up with these multi-states. So from a particular state, a transition will actually take you to many successor states, which is a bit like what happens in rewriting in the abstract, but it's not based on rewriting. It's just based on these finite state machines. But in that world, you actually kind of collapse the system down into just a regular, or sorry, I should say standard, not deterministic finite automata. So it was and that's where you do the power set construction thing, and you go from DFA to NFA. So it's a very simple example, and it's, I mean, for some people it might be more intuitive, maybe not. And I had some other thoughts about it. I liked the numerical multi-way systems stuff. I spent a long time playing around with that. And those fractals I showed at the last thing, when I showed them to Stephen, he was like, oh, it's just a numerical multi-way system. So that's an example of like, yeah, you're applying sort of a set of arithmetic or whatever operations on your state, but you get this interesting sort of connectivity structure, and you get these multiple edges from a particular number going to some other numbers.
Stephen did it with collats. You can do it with like the reverse collats thing, so you can start from 1 and build the collats graph from that. So yeah, in that's another way in which you can have these multi-computational aspects without rewriting.
Yeah, so maybe just to share some of my ideas there, when you spoke about uncertainty and what you would say in like a multi-computational case where there's like splitting of paths, so you talk about quantum, having like, okay, it could go this way or it could go that way, but you just run them simultaneously and like as if both possible things happen, but with some probability that you can determine once you have the result. But there's also an uncertainty with regards to like computational irreducibility of maybe a deterministic cellular automata, where the only way to determine where something is after a certain time step is to actually run the computation. And is there some kind of difference there? And is that multi-computation if it's just a case of like not knowing because you haven't run the rewrite rule enough? Do you know what I mean? Like,
I can tell you how I like to think about this uncertainty thing. There's like two flavors of it. There's like an intrinsic and extrinsic one. And like in the multi-computational system case, like intrinsic one is just means that it's like inherent into the system, and because you have this ambiguity of rewriting rules applying, right? And it's like rather an extrinsic because I applied. It's an extrinsic rule, the ambiguity. But intrinsic is the uncertainty for the observer embedded into the system. It's just the informational part of this uncertainty. So how one part of the system is just unaware of some other part, or aware of it only to some particular degree. So he has some beliefs about the part of the system, and that's how you can describe the quantum state. So basically, this intrinsic one is just when an observer is uncertain about some system, can only lead to some classical uncertainty. It seems like it's just probabilistic knowledge that's being updated with interactions of an observer with the system he's observing, right? But this extrinsic uncertainty embedded into the rewriting using some different paths so that an observer can actually branch, right? So that the observer just happen to be on two different branches and he doesn't know which branch he's actually observing right now, right? So that's like this kind of uncertainty leads to different effects. And so that's kind of the idea that the extrinsic uncertainty leads to quantum theory. That's the difference between two flavors of uncertainty that you can extract from these computational rewriting systems.
So does the multi-computational approach only apply to the extrinsic version?
No, it emphasizes that one more.
Okay.
But it's like in any computational system, you can, as soon as you want to explain or explain the observer, so as soon as you start building observer theory, even without any branching, you can have uncertainty.
Yeah.
But as soon as you have multi-computation, you're emphasizing that there's observer can exist like in multiple paths.
Yeah, I'm trying to think if those things aren't somehow related. Is that the existence of multiple paths is what creates all uncertainty, but one of the like paths that are time dependent is what creates the intrinsic state. So in other words, it's not necessarily like where the observer is, but it's kind of like what the observer is experiencing over time determines like which category in. Yeah,
the observer, like for the observer himself, it's like he's unaware of which type of uncertainty he's dealing with. He's dealing with at all. So it's kind of that's why quantum theory in its most natural sense, it's almost undistinguishable from just probability theory. There's just some quantitative differences. Right? There's like I showed last time, there's just some different geometries of what you get for the probability theory and the quantum theory. So it's just the way probabilities are manipulated are different. So that's basically what quantum theory tells you. It's the nature of those branching, right? So how it is different from just having some uncertainty about not interacting with that system of particle with the most efficient way. right? So it's like that's why quantum theory is always says that there is like inherent uncertainty. There's like h bar, right? So that you can't know something about your system more than this limit. So it's a natural limit of uncertainty. Even though it's like, but it only arises when you have this kind of branching.
What's the h bar? What is it stand for?
Oh, it's Planck's constant.
Oh, okay.
H bar. Yeah.
The h bar. The natural limit for uncertainty.
And then you were saying that that's related to multi-computation?
No, that's the idea. I wouldn't claim that I know what the exact relationship is, but yeah.
Interesting.
Yeah, we'll have to
Well,
get there.
okay, that was a great chat. Covered a lot of topics there, and yeah, the big thing is looking forward to the workshop. As Carlos mentioned, you can attend virtually, so join the Discord to find out about how to join that and interact with the community there. Yeah, it's going to be awesome. The one we did last year was like great success. We learned a lot. There was some very interesting concepts that came out of that. And what's nice with these big events is that this is sometimes where progress gets made in these fields, because you have experts from various areas that get together and share some of the stuff that they've been working on, which potentially no one else is working on. And that cross collaboration, cross pollination happens at events like this. So get your seat on the front row, whether it's in person or online. And yeah, that's the idea. Next stream is on Friday, Carlos.
Yes, that's right.
Yeah. Oh, you're on mute.
Sorry, yes. Yes. No. Yes. So on Friday, I mean, this is another announcement, technically, that we are finally going back to infrageometry after some break and some different directions pursued, and we are finally going back to it. So hopefully, I think Nick will be joining us. Are you available then, Nick?
Friday, yeah, sure.
Yeah. So we'll be covering some basic definitions. Oh yeah, very nice. And hopefully setting out the new directions. And the expectation here is to recover what calculus means if you don't know about real numbers. So it's a good short-term target that we're trying to get. That's also what Stephen initially pointed at. He called the project infracalculus, and we were not very convinced with the name, and so in the process of understanding the physics project foundations a bit better, and generalizing the fact that the calculus that we really need is the one that happens on manifolds and so on. Let's say, okay, let's do something that we call infrageometry. So we give a sort of discrete foundation to something that looks like geometry, but it's purely finite, purely computational. And the goal is that if we get to something that resembles, or that we morally believe to be the discrete instantiation of calculus, and with the fundamental theorem of calculus as the sort of main goal, then we'll be thinking that we're on the right track. But for that, we have a lot of ground to cover, so we're doing a live stream on that on Friday. So looking forward to seeing all of you there.
And what's nice is people can help us in the comments, know. So there's many people here with great ideas that can assist in that live science. So come and take part.
Definitely, yeah.
Great.
All right, everyone.
Okay.
See you soon. Cool.
Thanks. All the best.